All right, so I only asked you guys to do 2 pages. Guys, quiet, thank you. I only asked you guys to do 2 pages, pages 5 and 6. So basically number 1 of the handout B. So when you see something like this here, r squared equals 25 sine 2 theta, that's going to be what we call lemniscate. That's the term we use to describe this graph. And it's kind of like a dumbbell in a way. An interval from 0 to 2 pi, the starting point. So obviously if you plug in 0, r squared will be 25 times 0. So r squared is 0, r is 0. So your starting point 0, 0 right at the pole. And determine the symmetry. Well, because you have a point at the pole, we're probably going to be symmetric about the pole. So we're looking for pole symmetry. For pole symmetry, you want to try negative r comma theta. And I do have a handout, a copy of the solution. So I'll scan that and put it in Schoology for you guys. So if you replace r with negative r, well, you're squaring it, so it gets back to being r squared again. And theta you just leave alone. So the right side stays as is as well. And therefore, you get the same thing. So you have the symmetry at the pole. If you were to graph it, there'd be a point at pi over 4, comma 5. Because you plug in pi over 4, sine of pi over 2 is 1. We know this, right? So you plug in pi over 4. If I do r and theta, a little table here. If I plug in pi over 4 for theta, r should be 5. If I plug in 3 pi over 4, no, I take it back. Because that would be 3 pi. Actually, no, if I do that, that'd be at negative 5, right? Wait, let me take it back. Hold on a sec, sorry. Sine 3 pi over 2 is negative. Oh, that can't work. That can't work. Because r squared can't equal a negative number. So that actually that's no good. 5 pi over 4 I could do. Because I do get back to I get back to 5. But it could be plus or minus 5. Yeah, right. That could be plus or minus, that's true. So you definitely have points here and here. So 1, 2, 3, 4, 5. So the graph will look something kind of like this. That's what we see there. Terrible looking drawing. I know I could do better, but it is symmetrical about the pole. If I rotate 180, I get back to the same orientation. Dude, go ahead.
So because it's plus or minus 5, you set the range of theta values to just be the first quadrant, and it would cover the whole.
You could, yeah, you could. Now for D, you'd be good.
It'd be symmetrical by the whole theta equals 5.
It is. Yes, that's correct. Right. And Brady, go ahead. Yes, you can. Yeah, that could work too. Okay, guys, quiet, please. So then to determine the zeros, 0 equal 25 sine 2 theta. So sine 2 theta equals 0. Or 2 theta would equal 0 or pi. So you have 0, pi over 2, also 2 pi. When you divide by 2, you get this, and also 3 pi over 2 and 2 pi. So I'm getting 5 answers. That'd work. And then determine where it crosses theta equals 0. Well, we already know that's theta equals 0. That's r equals 0. At theta equals pi over 2, that would be at 0 pi over 2. And again, that's a 0, 0 for that. And also, you do want to investigate what's happening at pi and 3 pi over 2 and 2 pi. At pi, it's going to be 0 pi, 0, 3 pi over 2, and of course 0, 2 pi. So, questions? Yeah, go ahead.
What those reduced out to range of theta values from pi over 2 to pi, and where are those coordinates?
Sorry, from what to what?
From pi over 2 to pi, so 7 pi.
Okay, well, the problem there is that if you do plug in, those are going to be negative values. So you can't see, you have nothing there.
In the third, second quadrant.
But there's nothing in the second or fourth quadrant, so.
So there's anything in the second, fourth quadrant.
Right. Just given the nature of the equation, because you have 2 theta. So if you plug anything between pi over 2 and pi, that's going to be, it's like taking a sine of an angle between the third and fourth quadrants, which sine's negative there. and then therefore r squared is negative, you can't have that because it'd be imaginary.
That makes sense.
Right. That's why you don't, that's why you're not, that's why you're seeing some parts don't have anything. It so happens it's the second, fourth quadrants given the nature of the equations. Sure, go ahead.
You just have to like look at graphs and just, okay, well, it's gonna be 0 here.
Correct. Right.
Okay, and then, so 2 pi is in the range, even though if you divide it by 2.
It would be. It would be. All right, for number 2, this is what we call a dimpled limicon. We're going to go from negative pi to pi. So determine the starting point. Obviously, you do 3.5 plus 2 sine negative pi, which would be 0. So you get 3.5. So 3.5 comma negative pi. So 3.5. But if it's negative pi, it goes this direction. So that's, let's see here, 1, 2, 3. So be over here somewhere. And if you were to do the rest of the graph, let's do a little table here. If you plug in pi, you should get 3.5 as well. So it's basically the same place again. Let's plug in 0. Again, you get 3.5. So that should be over here. If you plug in, say, pi over 2 or negative pi over 2, pi over 2 would be 5.5. Negative pi over 2 would be 1.5. So pi over 2 and 5.5, that's 1, 2, 3, 4, 5 right there. Negative pi over 2, 1.5. So it's kind of like that. Is that what you guys got? Okay. Determine the symmetry. It's definitely symmetrical pi over 2. So you want to try perhaps this. To verify that symmetry, you should have 3.5 plus 2.5 times sine of pi minus theta equals r. Well, sine of pi minus theta, that's in the second quadrant. That's still going to be the same thing. So it's verified. If you plug in 0, guys, quiet, you're not going to get anything because you wind up getting this. So sine theta will be negative 3.5 over 2, and that's impossible. Can't have that. And then E, fine for E, plug in 0 and pi over 2. And while we're at it, we'll also plug in negative pi, and negative pi over 2. While we're at it. So I'll plug in, let's see here. Theta equals negative pi over 2. Theta equals pi over 2. Theta equals 0. So you should get, for negative pi over 2, you should get 1.5. I kind of already did this, but I'll do it again. Yeah, yeah. I mean, usually those are kind of significant points, like at the at a different boundaries for each quadrant could work. That's negative pi. So that's going to be 3.5 negative pi. 2.5? No, it's not 2.5. And 0 should be 3.5 comma 0. And that's all for this down here. Yeah, UV, go ahead.
So the zeros are what r is equal to 0? The zeros are no, moving it.
No, I already did part D. You missed it. There are no zeros. Yeah, I just ran out of space. That's all. Brooke, go ahead.
Wouldn't the F not include when it intersects pi over 2? Just like take out.
No, pi over 2. Yeah, no, you're good. And then lastly, what range of values we'll produce the part that's above theta equals 0. So above like kind of like the x-axis. That'd be, so part F would be from 0 to pi. That proves the top half. We're good.
So are zeros just where it intersects theta?
Exactly, 100%. Right.
But we're so.
Oh wait, no zeros. Those zeros when R is 0 when it touches the pole. Sorry, when it touches the pole. Right. All right, let's keep on moving, guys. So let's get the notes out. We're going to talk about Rose curves. And are there any questions from the notes from the video I made a couple days ago? No? No, we're good. Okay, we're going to talk about Rose curves. Those are kind of the cooler ones. I feel I like kind of like that more than the other ones. And then we're going to move on to part 3 today of the notes. So we got a lot to do, guys. Okay. Oh, what time do you guys leave on Friday for your WARPA?
I don't think we. No, we don't miss your class.
Okay. Yeah, because you're driving out to Stockton, right? Yeah, so that's a long trip. How come they can't play at a nicer area? Like, why Stockton?
No, last year was home advantage, higher seat. So we played all North.
I mean, I guess. I mean, is anyone from North that you're playing that you would play? Like, because you would play either Bellarmine or who else?
Bellarmine or Miracle. Well, we played De La Salle on Friday.
I guess Stockton's kind of close to them, but yeah.
All the students Stockton.
Yeah. I know, right? Okay. Anyway, let's get to work, guys. Oh, also just a little bit of planning. Just looking ahead, guys. Quiet down. So I haven't decided when I want to do the small test on the polar curves, but so it's gonna be another small test like the conics, but it'll be worth a little bit more because we cover more material. So the conics test was worth 40 points. So it's recorded as 40 points in Schoology. All the other tests prior to the conics was 100 points. It's because I broke up between the two small tests. In order, yeah, this will be worth 60 points to kind of give it equal weight. Kind of up to, I want to kind of get a heat check, kind of like what you guys are interested in doing when you think a test would be good for you guys. So I'm going to finish polar by Friday. That's the hope. I'll finish by Friday. We come back. I think we should do a little bit of review on polar. Make sure you guys remember everything. I would even be in favor of maybe 2 days review and maybe a test on Friday. Would that be okay on December 1st? Is that okay? Yes, no? Are you? You have no idea?
Do you know when I was gonna ask like how many weeks we have after Thanksgiving and before the finals?
3.
3 and then finals for Casper.
So our finals actually on December 15th. So we're doing finals different than all the other finals.
We have the math. I thought it was Monday.
Wait, our finals on the 15th?
No, so math gets a special day for finals because we do a traditional final exam. Other classes will have projects or papers or stuff like that. So on the 18th, let's start with A and B periods, C and D, E and F, and G. Now the good news is that since it's E period, you don't have a final on the morning of the 20th. Because guess what? You've already done it on the 15th. So you will get a free morning on the 20th. So if you have like a free F period, you have no finals on the 20th. If you have ceramics, you get no finals. Or if you have like a physics, okay, you can just focus on physics out there. So our final will be on the 15th.
Now, was that? Yes, it's cumulative. Now, I don't know the details of the file yet. I'll share that with you guys when we come back from break. But I'm thinking, guys, of this. Let's review polar on the 27th, review on the 29th, take tests on the 1st. On the 4th and the 6th, I do have to squeeze in just a little bit of new material from chapter 6. It's like on vectors. I'll just do won't be a test. I'll just kind of squeeze it in. And then we'll do 3 days of review on the 8th, the 12th, and the 14th. And then our final will be on the 15th. So that's kind of what I'm thinking in my head here. So
Is the final going to be 2 hours?
2 hours, but designed for 90 minutes. So it's kind of like a test and a half. And the weight, I think, is 20% of your grade. I have to double check Schoology. Actually, let me check Schoology right now. Hold on a sec. Shoot. Let me freeze my screen for a sec.
It's 20%.
It's 20%. Yeah, it's 20%. That's correct. Yeah, so it means that our 4 unit tests will all reach 15%. So this is slightly more than a unit test. Think of it like that. Was there a question? Yeah, go ahead. Yeah, I do have my Algebra 2 classes also. But I'll do an hour with Algebra 2, an hour with you guys. So I'll do that. And I'll be around that whole week of the 11th. Usually I don't work Tuesdays, but I'm going to be around that whole week because it is a big week. So yeah, I'll be available for you guys. I mean, yeah, it's like we have office hours on the 12th, we have office hours on the 11th, we have office hours on the 13th, we have office hours on the 14th. And I'll be available by Zoom on the night before the final as well. So anyway, so that's just looking ahead. So 1 day from today, sorry, 1 month from today will be the final. So, all right, let's get going to the lesson, guys. Here we go. All right, rose curves. Guys, quiet, please. All right, so we're going to consider these 4 functions: cos 2 theta, 2 cos 3 theta, 3 sine 4 theta, 4 sine 5 theta. We're going to graph this in the calculator, kind of emulate what the calculator shows us, and to try to come up with some sort of conjecture, right? So you might want to get your graphing calculator out. I'm going to do the same on my end. So let's get the calculator out, please, guys. Here we go. So no objections at December 1st, unit test on polar. No objections. Okay. All right. Yes. Kind of a little bit, but you won't have the undefined portion because you have the r squared and lemon skate. You have the r squared here. So you can get rose curves in every quadrant. Yeah. All right, guys. Here we go. Switch your mode to polar. Keep radians, of course. Switch the mode to polar. So let's do the first one. Oh, let me get my notes. Hold on. Guys, quiet, please. Thank you. All right. So we got ourselves cos 2 theta. Cos 2 theta. And let's 0 to 2 pi. That's all set. Let me reduce that to negative. We'll say negative 5 to 5 for x. And negative 5 to 5 for y, just so it's not too wide, the window. Oh, let's say 5. My bad. Here we go. And let's say 5 for x max. My bad, too. All right, cool. Okay, so there you go. So go ahead and copy that down in your notes. I'm going to type in the other ones. Just get them out of the way. 2 cos 3 theta.
What in the heck?
So let me turn off the first one because it's a little distracting. Okay, so you get that. There's 2 cos 3 theta. What do you think the 2 is doing, by the way? What do you think that 2 does? What will the 2 provide for us? The length? Petals. Yes. Okay. And we do see 3 theta, so we see 3 rose petals, right? But notice with 2 theta, I saw 4 rose petals. Interesting. Let's keep that in mind. Okay, let's look at sine. So let me turn off the second one. Type in a third equation. So let's do 3 sine 4 theta. Now, before we actually hit graph, I predict that the rose petals will have a length of 3. That kind of makes sense. The orientation might be different. And we'll see how many petals we get.
Oh, wow.
We have 8. Okay. So we had double the coefficient of theta. Okay. That's interesting because we had even coefficient for theta for the first one, and that was double the petals. Here we have another even coefficient with double the petals. The orientation is also a little bit different too because it's sine, not cosine. Cosine happened to be on the axes except for the cosine 3 theta. And then lastly, and I'll draw all these for you guys in just a sec. Let me turn off this. Let me turn this one on. 4 sin 5 theta. So I'm probably going to have 5 petals, length of 4. So it's like a pentagon in a way. By the way,
If you think about it, full circle 70 degrees. You're 16 divided by 5, you get 72. So this is probably 72 degrees between the first petal and the second petal. So it means that this is probably 18 degrees, 90 degrees. That's probably 162. Yeah, there you go. And then, I don't know. 3, 4, 7. Yeah. There we go. Makes sense. Yes, actually, good mental math. Good. All right, so let me draw these in for you guys, just to make sure we're all good. Okay, let me zoom out a tad so I can squeeze all 4 of these in at once. All right, I'm going to do my best with steady hands. I should never want to be a surgeon. I'd be terrible at it. Okay, you guys remember that game? I'm not sure. This is back in the 80s. I'm not sure if you guys ever saw it. It's called Operation, where you have to like, there's like 5 parts, and you have to like use the tweezers. I was awful at the game as a kid. I was terrible at it. I was also terrible at scissor cutting. I failed scissor cutting in kindergarten, so terrible at that too. Yeah, I think on N need improvement. Okay. Okay, so that's pretty obvious for that one. This one's gonna look like this. Okay, seems to make sense there, right? And this would probably be at 2, 3 pi over 4, I'd say. And this would be at 2, 5 pi over 4. No. I'm losing my mind, guys. Sorry. I'm gonna say 2 pi over 3. That was dumb. 2 pi over 3 because we won 20. And 2, 4 pi over 3. There we go. I feel better about that now. That makes more sense. And of course, that's 2, 0. And these here were at 1, 0, 1, pi over 2. 1, pi. And wait, am I correct in saying that? Actually, it's really technically -1. Actually, hold on a sec. Yeah, and that's, geez, my handwriting stinks, guys. Sorry about that. Yeah, that'd be -1, 3 pi over 2. Just got to flip.
Oh, because it's going.
I'll explain in a sec. Okay, let me explain what's happening here.
5.5, that's 2 pi. Those have 2 pi's. 1, 2, 1. That makes sense, right? Because your pi, revolution, capital pi radians. 1, 0 makes sense. You plug in 0, goes in 0, 1, 1. So these two make sense on the x-axis or the theta equals 0, polar axis, if I say that. Now, pi over 2 is interesting. Plug in pi over 2. 2 times pi over 2 is pi. What's close to that pi, guys? -1. So you're here, that's -1. Jumps. Then 3 pi over 2, 2 times 3 pi over 2, 3 pi. Close to 3 pi is -1. So 3 pi over 2, you're going to do that. 3/4 turn. So r is -1. Jump. So technically speaking, that's actually -1 pi 3 pi. That's -1. So that's, if you were to label it correctly, that's how the labels would work. For the sine curves, remember we had something kind of like this here. These kind of look like actually those balloons that like you get at carnivals. They charge you like too much money to pop. Okay, so if you think about it, that dashed line that I just drew is theta equals what, guys? That dashed line I just drew. Right. So then these dots here, the radius, of course, is 3, and that's going to be pi over 8.
So it's actually 22.5 degrees. Because if you think about it,
What's 360 divided by 8? That's 45. But because of the orientation,
you're not doing it 0 and 45. You're doing it in between 0 and 45. So this would then be 3 comma 67.5 or 3 pi over 8. I'm not gonna draw the other ones because it just takes, or label the other ones because it takes too long. But 3 pi over 8, 3/8 is half between 1/4 and 1/2, right? So that's how the orientation will be for that one. And then here, remember we said that this is 18 degrees, right? And that was 90 degrees. We'll convert that to radians. That's going to be pi over 10, right? Because pi is 180, right? Pi radians is 180 degrees. So if you have 18 degrees, that's pi over 10. So the point here will be 4 comma pi over 10. And 72 degrees, if you convert that to radians, that's going to be what? 72 over 180, 36 over 90, 18 over... is that pi over 5? Yeah, pi over 5, right? Am I correct in saying that? No. Hold on. No, I'm right. I got that. Yeah, it's pi over 5. 72 degrees, pi over 5. Yeah, it's pi over 5. So that goes pi over 5 radians each direction as you go around the whole circle. So, yeah.
Why does it go over it twice?
For sine?
Yeah.
3 sine 4 theta. Well, if we were to make a table, that's really kind of the best way to investigate. If you do r and theta, and I mean, I could do it, it's just going to take a while. If you plug in pi over 8, because of the 4 theta, because you're going from 0 to 2 pi, it's really more because of the fact that you have the even coefficient. Those row spells occur twice. But if you were to actually make a table and go from 0 to 2 pi, you're going to start noticing a bunch of different places where you get the maximum value for sine. Because you have to think about the end of the rose petal is the maximum value for sine, right? So the maximum value would be, for r would be 3. So max value for sine would be 1. So bottom line is you want sine 4 theta to equal 1, right? So 4 theta equals inverse sine of 1. What's the inverse sine of 1? Pi over 2.
Yeah.
So 4 theta equals pi over 2. And you have to do this, you have to get all possibilities from 0 to 2 pi for theta. So first would be pi over 8.
Yeah.
And then set equal to 5 pi over 2, set equal to 9 pi over 2, set equal to 13 pi over 2. All those situations are all going to be from 0. And then as you keep going, you start noticing that you get more and more values.
Yeah.
Likewise, if it equals -1, if sine is -1, hold on, Ryan. Because then you flip it over with the negative r value. So yeah, so you have more responsibilities. Ryan, go ahead. Yes.
Negative 3 pi. For the ones with the sign, when you want to find like the, I guess, the theta coordinate, you just put pi over 2 divided by the.
Right, we're going to talk about that. Right, exactly. For the cosine's easy. You start at the you start on the positive polar axis at theta equals 0, and then you just kind of divide that by 2 pi, 2 pi over 3. So you just go 2 pi over 3 all the way around. And for cosine, if it's even, then you don't make petals. There are 4 petals, so you do 2 pi divided by 4. So pi over 2 is pi, 3 pi over 2 back to 2 pi. So for sine, right, you're gonna have to shift it, right? So in this case, for 5 theta, just trying to think here how I would place that one. It's a little tricky. I guess what you could do if it's odd is like you have it one at pi over 2, and then you just kind of go and then just divide up, do 2 pi divided by 5. So you do 2 pi divided by 5 all the way around. Okay. Which is actually wait. No, that was supposed to be 72 degrees. Hold on, Jeff. The 2 pi divided by 5 would not be that, that would be 144. I think you should do pi divided by 5. You do pi divided by 5. Whereas this case here, it is shifted a little bit. So you have 8 petals. So And you're not actually doing one on that axis. So we'll talk about those generalizations a little bit, but for now, just realize you're gonna double the pedals with an even coefficient of theta. The exact number of pedals was odd coefficient of theta. The number in front of sine or cosine is the length of the rose petal, and cosine starts on the theta equals 0. Sine, we have to make some adjustment. We'll talk about the adjustment because I'm not 100% sure about that generalization. Duke, go ahead. Cardioids. Lemniscates, yes. Go ahead. Right.
So is it like this with like minus theta? So the reason it's pi over 8.
Well, I think it comes down to the symmetry also, though. Let's hold off on that.
I think it works was the last example like was sine 5 with us.
Right.
It's shifted like the first pedal is shifted pi over 10 up as it's like pi over 2 minus theta, but
So,
whatever value you can see pi over 2 your maximum radius.
no, I know that. With that, we know. He's asking about something else. Where he's asking where the theta starts. So I mean, I guess we could do is you could do 2 pi divided by that number. We have to do an adjustment also because it's sine, not cosine. And that's the part that I'm not 100% sure where exactly to generalize that. So let's work through the rest of these examples and we'll come up with that. So anyway, all the equations have that form: r equals a cosine theta or r equals a sine n theta. So a impacts the length of the petal. We know this now. A is the length of the rose petal. These are petals, not leaves. And if n is odd, then you have n petals. If n is even, you have 2 n petals. Now, this is what you want. This is what we're trying to get at: the orientation for sine versus cosine. Okay, let's talk about it. For cosine, always the petal on the polar axis. Remember, the polar axis theta equals 0. And always symmetric about theta equals 0, or about the polar axis. So remember, we had this, right? Or we had this. So theta equals 0.
So it's right in the middle of these, right? Kind of like the x-axis, right? Always be symmetric about that. Not guarantee you'll be symmetric about theta equals pi over 2. Definitely was here, but not here. So, but guaranteed cosines will always be symmetric about that.
Now sine. The one thing we can really say about that, symmetric about theta equals pi over 2. So remember we had like this here. It's really messy, sorry. Or this one, we had that. That's a little better. I kind of really messed up this one pretty badly. But you get the point, right? So that's what's happening with that one. And then we're almost done talking about rose curves. For E, let's see here. Okay, so looking back at the graph of r equals cos 2 theta, it appears to be symmetric about the pole. Convert that algebraically. Well, to be symmetric about the pole, we could try r comma theta plus pi. No, that's the only thing we could say for sure. That's the only thing we know for sure for that one, because you can't say it's symmetric about the polar axis. That wasn't true for 5 theta. I mean, I guess you could say it's symmetric about, is it symmetric about theta equals, or symmetric about the pole? Not always. Because you want to be able to rotate 180 and get back. No, that's not true. You can't say it's always symmetric about the pole. But for cos 2 theta, we can. If I do this, r equals cos 2 times theta plus pi. So then you get cos 2 theta plus 2 pi, which of course 2 pi goes around, right? Or if you want to do the sum difference formula, you could. About the pole. Yeah, the pole is going to be, you try that.
Why can't you try negative r, comma, theta? Like, why doesn't that work?
I don't think we do that for, actually, sometimes it doesn't always work. Actually, you are correct. Sometimes we can do that, but so you try one of the two that makes it work. So, no, you are correct. I mean, because we asked to find symmetry about the pole. Just yeah, that's all. Okay. All right. I think that was it about rose curves. I'm not sure if there's anything more we want to say about that. And honestly, to figure out where to start these, I mean, you're symmetric about pi over theta equals pi over 2. Because I'm symmetric that way, like when I have 4 theta, I know I need 8 petals. The only way to guarantee that was put 2 petals in each quadrant for sine 4 theta. So it just kind of depends on the situation you're given. All right, guys, we're moving on to part 3 now. Let me just check time, make sure we're okay. Today is the 15th. Yeah, let's keep going, guys. I want to keep moving here. All right.
I'm just looking at that.
Okay, I'm gonna fill out the same line you guys filled out too, right?
Here we go, guys. We're trying to fall together. All right, here we go.
I swear, bro.
With interloop. Let me just, you know what? I'm gonna type it up. No, you guys are correct. I should. All right. Oh, look at that.
That's perfect.
Yeah, it was perfect.
Demonstrate.
But the fun is like the grip is something. It makes me feel like I'm scared.
Yes, up.
Can you sharpen this in a moment?
Yeah.
You have to shift the thing. If you wanted to own practice, actually use one of the other holes. Are there other holes? Not that one.
Okay, I think I'm gonna go back to handwriting now. I'm sorry. I think I should be able to read the rest here. Parabola.
Oh, you. Where's the X? You.
Okay.
So these are graphs that we've already done. Not gonna do them over again. So your notes show these equations. So I show graphs of these equations. So we see something like this here where A is less than B. So A plus B cos theta, that is in loop. Remember the length of the loop was 2. And the bigger part was 1 plus which is 4. This produces what we call a cardioid, kind of like heart. So it kind of caves in a little bit, right? And we had dimpled, not quite a cardioid. This is what A is bigger than B. Or the fraction of A over B was between 1 and 2. We talked about that. Well, actually, I talked on video. And then when the fraction between A and B is greater than 2, that's convex, meaning there's no caving in that case when it's convex. Cosine has horizontal orientation. Sine has vertical orientation. And if you were to think of it like a conic section in terms of in that regard, r equals 1 over f of theta, you actually would produce conics. So basically, if you took whatever the function is in terms of theta and did 1 over, so if you did 1 over this expression, 1 over this expression, 1 over this expression, 1 over this expression, we're actually going to generate conics. We're going to talk about that. So we're connected to back to conics. You'll see in a little bit. We'll talk about it. Do good. Bigger than 2, yes, correct. Okay, so here we go, guys. If a limicon has a loop, it's a hyperbola. So generally we're calling these limicons, but these are special type of limicons. If it's cardioid, the conic is a parabola. And then the last one, if there's no loop, would be an ellipse. A cardioid what? Not quite, but it does cave in though a little bit. So that's, and it's not convex, right? Because it does cave in. Okay. And it does somewhat tie back to eccentricity, which I know I didn't talk much about with you guys, so I'm not going to really traverse down that path. But let's look at the next page, do a little more generalizations, and we'll do some problems, and then we should be done with these notes in about 10 minutes. All right, so generally speaking, if you take these polar equations, r equals a plus b cos theta, r equals a plus b sine theta, and put a constant on top of them, so k over the a plus b cos theta, or k over a plus b sine theta, then what's going to happen, if a is less than b, you have hyperbola. If a equals b, parabola, which is a cardioid, a bigger than b will be an ellipse. So in the case of A, that's totally going to be hyperbola. In the case of B, it's totally going to be a parabola. Now, you're asked to convert back to rectangular conic standard form. So it's all algebra, right? So before I do it, take a step back, deep breath. What do you think I should do against it? Yeah, let's do that first. By the way, I'll do it on the board, but we're gonna do it here for Adi. So, and for you guys who just watch. That's correct. You have. Okay. And let's distribute. Okay. Now, before we go any further, take a deep breath. Please stay through. The R considers what the important. X, right? That's X. Okay. Okay, so 3x. Okay. So I'm not gonna go too crazy here. Just hit 3x. And what about R? R squared is x squared plus y squared. So root x squared plus y squared. Exactly. Right. You do that. Or let's back up a little bit more. Maybe you didn't know what to do with this R. That's fine.
move the 3x over. What do you think I should what should I do algebraically now?
We're both sides.
Square both sides, yeah, totally. And then you could substitute, you don't have to even deal with radicals at all. So r squared or x squared plus y squared. Now, I think you guys should be comfortable.
Because now it's all rectangular, right? There's no more floor nonsense around the window. Now I think you guys are comfortable with completing square to get it into standard form. And we know, so it's a hyperbola. So it's supposed to have x something, or some x squared y squared with one is negative and one on the other side. So
Now this is where it gets a little crazy. But at this point, you guys are fine. You guys have already done this. X squared plus y squared equals 1 minus 6x plus 9x squared. 0 equals 8x squared minus 6x minus y squared plus 1. Let me take a step back again.
Does that make sense? That group correctly, 8x squared. Yeah, everything's going to be okay, right? This is not a fun one. It's 100% annoying. And I'm just going to do it on the board, so I'm not going to, it's just going to be a little crazy. So I'm going to factor in 8. That becomes 6/8x. And y squared is y squared, that's easy peasy. Plus 1. Well, 6/8, what does that reduce to? So you can square half of it, which is 3/8. Square it, which is 9/64. Did I get it right? But what did I really introduce? I really introduced, if I put it back in, I really introduced 9/8. But bring that one over, that's 1/8, 8, x minus 3/8 squared minus y squared. And then I'm going to multiply both sides by 8. So we get 1 equals 64. Which really, oh boy, is this? X minus 3/8 squared over 164 minus y squared over 1/8. That's really.
So I'm just going to put the answer up. I'm not going to ask the graph because it's too crazy to graph. Yeah, so there you go. I know the center is at 3/8, 0. And I could, if I want to find both sides asymptotes, but let's not worry about that. It's just too crazy. So, okay. Why don't you guys try part B in your table groups? We'll check in about 3 minutes, see how you guys are doing. Try part B in your table groups. God bless you.
I got x squared plus y squared is equal to 4y squared plus 10y. Yeah, I did get a pro. I didn't get a pro. No, you're supposed to get. No, you're supposed to get. A equals B.
Oh.
So where did I go? I don't know. Am I just writing this?
No, I'm pretty sure you're supposed to get out.
Oh. Oh. That's it, 2 feet apart. Oh.
Okay, so where do I want to be? Oh, no, I see it. No, I'm supposed to.
Okay, here's what I got, guys.
You got the same thing.
I just swear to God, without swearing. Yo, I got it right.
Yo, the 16x, the 16x squared minus
I know, someone is right now.
So remember, the standard form for a parabola is x minus h squared equals 4p y minus k. This is a parabola that's going to open vertically, right? So it's 4p times y minus k. Right. So we usually want these to have set that way.
Wait, what if you're wrong if you did like slide?
No, you're not wrong. Nope, you're still fine. That works too. Yeah, that works. But I just read it, so it's this way how I shared with you guys in the formula sheet. So. And by the way, I'll give you guys that formula sheet back again for the conics. I'll give that back to you guys again. So, okay. Given that the class is over in about 5 minutes, am I correct in assuming that?
Yeah.
And the next notes is actually not too bad. I could probably knock this out on Friday. And the homework is not going to involve part 3 of the notes just yet. We'll stop there today, guys. So I'll do the rest of these notes. Page 21. Sorry, page 20. I'll do the rest of that on Friday. So I don't want to rush this. But we should have plenty of time to get all this done by Friday. Homework is just, guys, quiet, please. Actually, I'll stop right now.